Welcome to The Explainer. Today, we're taking on the ultimate cosmic cold case. How does everything actually end? For millennia, the end of the universe was basically the exclusive domain of mythological beliefs and theological eschatology. But today, well, we've replaced those untestable ideas with hard, observable science. We're going to look at the facts, the data, and the absolute most compelling theories about the ultimate fate of our cosmos.
Let's start with what we know for sure. Thanks to astronomer Edwin Hubble's completely groundbreaking observations back in the 1920s and 30s, we discovered that distant galaxies are actually moving away from each other. And this simple but honestly profound observation led to the Big Bang theory. It tells us exactly how many years ago the universe began in a highly dense state. 13.787 billion years ago, to be exact. So we've got a pretty firm grasp on our origin story.
But here's the thing. We know when the clock started, but how much time is left? Okay, let's dive into this, because this is the ultimate mystery of our future. To figure out exactly how the universe ends, we can't just look at the stars. We actually have to, in a way, weigh the entire universe and figure out exactly what it's made of right now.
The answer, it turns out, is completely hidden in the invisible forces of the cosmos. To solve this cosmic cold case, we first have to interrogate the really mysterious ingredients that make up our reality. Because it's not just the planets or the gas clouds or the galaxies that matter here. The major players that are actually dictating our future, they're entirely unseen.
And this brilliantly illustrates exactly what I mean. When we break down the composition of the cosmos, the normal matter, literally everything we can see, touch, and interact with, is just a tiny sliver of the pie. The universe is actually dominated by dark energy, which makes up roughly 68% of the total energy content. Dark energy is completely in the driver's seat of the universe's expansion, acting like this massive repulsive force pushing everything apart. And then we've got dark matter, which exerts a gravitational pull, basically trying to hold things together.
But wait, if we can't actually see dark matter, how do scientists gather these clues in the first place? Well, they use this absolutely incredible phenomenon called gravitational lensing. Since dark matter has mass, it literally bends the fabric of space. So when light from distant galaxies passes by this dark matter, the light bends. It's kind of like looking through a giant cosmic funhouse mirror. By measuring that distortion, gravitational lensing acts as a super powerful tool for probing the elusive nature of dark matter, and it allows us to map out the invisible mass that's pulling on the cosmos. So the crucial point is that the key to solving this whole mystery lies in a concept called the density parameter, which physicists represent with the Greek letter omega. This is the absolute linchpin mathematical clue predicting our fate. It's simply the average matter density of the universe divided by a highly specific critical value. And why does this matter so much? Because this single, very specific number mathematically dictates the physical shape and geometry of the entire universe.
Think of this like our cosmic suspect board. We've got three possible geometries for space here. Depending on the exact value of omega, we get three distinctly different potential realities. If omega is greater than 1, space is closed, sort of like the surface of a sphere, meaning parallel lines will eventually meet. If it's exactly 1, well, it's flat, like a piece of paper, and those parallel lines stay equidistant forever. And if it's less than 1, the universe is open, shaped kind of like a saddle, where parallel lines actually grow apart. The ultimate fate of everything hinges entirely on which of these environments we actually live in.
The incredible thing is, modern cosmology has actually given us a measurement for this. Data from the Wilkinson Microwave Anisotropy Probe, or WMAP for short, combined with other observations, has confirmed that our universe is flat, and that's within a remarkably tiny 0.4% margin of error. It is walking a razor-thin line, perfectly balancing on omega equals 1. And knowing this flat geometry strongly points us toward interrogating our first major scenario.
Let's move to and see how this builds into our primary suspect. Scenario 1, the Big Freeze, which is also known as the heat death of the universe. Based on our current measurements of an expanding, flat universe that's dominated by dark energy, this is by far the most scientifically supported conclusion. Though I have to warn you, it is a slow, quiet, and pretty bleak end to the cosmic story. Here's exactly how the Big Freeze plays out. The universe's expansion just continues indefinitely. Trillions of years from now, the gas needed for new star formation will be completely exhausted. The existing stars will slowly burn out, and the universe will just grow completely dark. Black holes are going to dominate the cosmos, but even they aren't eternal.
right? They'll eventually evaporate over unimaginable timescales by slowly leaking mass via Hawking radiation. So the universe will slowly, inexorably cool, approaching absolute zero. Entropy basically reaches its absolute maximum, which means the energy gradients you need to sustain any form of information processing or life simply cease to exist.
Now, if the big freeze is this sort of quiet fading into the night, scenario 2, the big rip, is a sudden, terrifyingly violent conclusion. It offers a really stark contrast to the slow fade of the freeze. It represents a drastically different fate, and one that depends entirely on the unpredictable nature of dark energy. Now, what's really interesting about this slide is what actually triggers this violence. It's a hypothetical form of dark energy called phantom dark energy. If this phantom energy causes the Hubble constant, which is the rate of expansion, to accelerate to infinity, the expansion of space becomes so extreme that it overpowers literally all other forces. First, entire galaxies disintegrate, then solar systems and planets are torn apart. Eventually, in a finite amount of time, it completely overwhelms the electromagnetic and strong binding forces, literally tearing apart the very elementary particles that make up reality.
Okay, let's shift gears entirely here. What if the repulsive force of dark energy doesn't just win forever? Imagine a scenario where gravity actually wins the cosmic tug-of-war. This brings us to scenario 3, the big crunch and the big bounce. This is essentially a cyclical model of the universe, asking us to imagine if our inevitable end is actually just a mirror image of our explosive beginning.
So let's walk through the timeline of this oscillatory universe. First, the current expansion slows down and eventually reverses entirely. The universe begins to contract, heating up and getting denser until everything collapses back in on itself toward a final singularity, the crunch. But here's where quantum mechanics steps in to save the day. The uncertainty principle might actually prevent a true dimensionless singularity. Instead of a hard stop, the universe might undergo quantum tunneling, sparking a bounce, basically a brand new Big Bang. Now, while current evidence makes this closed universe scenario a bit less likely, the mathematics mean it definitely hasn't been entirely ruled out yet.
Now, hold on, because we have to talk about the wild card. Colloquially, it's known as the Big Slurp, which, I know, sounds like a bad convenience store drink, but it is actually the ultimate high-stakes gamble, scientifically known as false vacuum decay. Unlike the freeze, the rip, or the crunch, this alternate fate has absolutely nothing to do with the expansion of the universe. Instead, it's all about the very fabric of reality fundamentally breaking down on a quantum level.
This theory basically posits that our universe might currently exist in a false vacuum. Think of it kind of like a ball resting in a small dip high up on a mountainside. You know, it seems stable, but it's definitely not at the absolute bottom. If the Higgs field, which permeates all of space, suddenly drops to its true lowest energy state, it triggers instantaneous vacuum decay. This phase transition could happen at literally any moment, completely without warning, expanding outward at the speed of light. It would alter fundamental physical constants, instantly destroying all matter, energy, and space-time structures as we know them.
I know exactly what you're thinking. That sounds absolutely terrifying, right? Is the universe completely doomed today? Well, let's ground this astronomical scale back down to reality and offer some reassurance. Even if a big slurp started right now somewhere out there in the cosmos, you likely wouldn't even notice. Because the universe is expanding and distant galaxies located more than 13 billion light-years away are moving away from each other faster than the speed of light, the vacuum decay bubble could never actually reach us. It simply can't travel faster than light. Therefore, most of the universe would remain entirely unaffected by a localized slurp. So, what does this all mean? Where does this leave us? Well, despite these brilliantly theorized scenarios, we have to admit to a pretty heavy dose of cosmic uncertainty. The universe has an incredibly complex inflationary history. The underlying physics of dark matter and dark energy are still incredibly enigmatic. If the properties of dark energy, its equation of state, shift again in the future, just like they likely did in the early moments of the Big Bang, our predictions could change dramatically. The dark forces driving our universe mean we are still essentially detective scientists working a very active case. Which brings us to a final thought. We live in this highly specific era, where the universe is cool enough to form stars, planets, and life, yet young enough that it hasn't faded into darkness or ripped itself apart. In a universe governed by invisible forces and inevitable ends, how does this fleeting, yet incredibly long window of existence shape your understanding of reality today? It's a profound mystery to ponder as we continue to look up at the stars. Thank you so much for joining me on this explainer. Keep seeking those answers, and I will see you next time.